Hi everyone, I welcome you all for our process measurement and instrumentation lecture series. Today's lecture is pressure measurement and instrumentation under the process measurement and instrumentation part. So this is our outline of online lectures. When we stopped for COVID-19 situation, we were about to do temperature measurement and instrumentation lecture. That lecture is, having a lot of examination questions, and it's a big part. So that is why I separately discuss all the examples on that part. So there's another video lecture on that, solving 8 examples, discussing some in semester exam questions also, previous ones. So please go through the 2 videos. So we will start today's lecture. So first of all, I would like to discuss about what is pressure. We all know, you have learned about pressure from school, I think secondary school. But clearly, I would like to revise it. The pressure is the force applied perpendicular to the surface of an object per unit area. So if the force is applied not perpendicular, you have to get the perpendicular portion of the force vector, right? So like that, that is how pressure is defined. Always pressure is going with the perpendicular force. That is important sometimes, because we have to when we have to discuss about the force and pressure relationship, as well as when we go to discuss about the strain gauges, this understanding would be important. Then how pressure is generated? Pressure is, if you explain it by chemistry and elemental physics, you can say that pressure is caused by collisions of molecules and particles with walls of container or a surface, or in between the molecules. So even though the molecules are moving all the arbitrary directions, but if we consider the pressure, there will be equal forces and equal areas of surface, and we will not consider the directions of the particles or the molecules that they are moving, right? So pressure is in fact is not a vector in that case. So you should not always think about pressure like force, like a force. So it's not a force. It's not a vector. So we will consider the force that applies on the surface perpendicular to the surface. So when we discuss about, when we think about a fluid, chemical fluid, or chemical might be a solid stream even. So if you think about the pressure applied, the pressure that you want to measure will not generate any vectorial relationship, right? Okay. Then we have 3 types of pressures, in fact: static pressure, dynamic pressure, and impact pressure. So I hope you have learned about these things, but please clearly demarcate your understanding. Static pressure, I hope if you have learned in fluid mechanics or fluid dynamics, I think you have clearly understood the static pressure and dynamic pressure. Even if you think about the kind of system that has several, you can think like a pipe network or something with the friction losses and all. So there you calculate the static pressure, static head, and dynamic head, right? So static pressure is the pressure of fluids or gases that are stationary or not in motion. That means simply the difference between the elevation difference, or maybe static pressure difference. If a certain chemical fluid is moving from one equipment to another equipment, so the pressure difference between the 2 vessels would be static pressure, one component of the static pressure. Then the elevation difference, so like that. Then dynamic pressure is the pressure exerted by the fluid or gas when it impacts on surface or an object due to its motion or flow. An example would be the friction losses, right? Or otherwise, if there is any other pressure caused by the movement of the fluid or gas, that is called dynamic pressure. I hope you can clearly demarcate. Then impact pressure is the sum of static and dynamic pressure. Otherwise, you can say it as total pressure. So this pressure can be represented by the units of pressure as well as the unit of head. So if it is, head means in meters or something. So you know that pressure is equal to h rho g. And if you try to relate it to the height, so you can say it as head. So then we can say static head, dynamic head, and impact head, like that, right? Then reference of pressure, right? So I hope you have learned about absolute pressure and gauge pressure. That is very important in equipment design also. Absolute pressure is zero reference against the perfect vacuum. I don't know whether you understand it. So in other words, if I say absolute pressure is the difference between the pressure of the fluid and the absolute zero of pressure, right? Absolute zero of pressure means you have to deduct the atmospheric pressure, right? So gauge pressure is zero reference against ambient air pressure, right? So normally what you can see as the pressure would be gauge pressure with reference to ambient or atmospheric pressure. So if you want absolute pressure, you have to deduct the atmospheric or ambient pressure. So the relationship between absolute pressure and gauge pressure, I hope you can understand now. So absolute pressure is equal to gauge pressure plus atmospheric pressure, right? Then differential pressure is the most important thing that is required for this this section. I mean, the pressure measurement and instrumentation. Differential pressure is pressure difference between 2 points. So all the, I mean, most of the equipment, most of the instruments, most of the pressure measurement devices are based on differential pressure. Differential pressure theory or principle. Otherwise, it is somehow measuring the pressure difference between 2 points, right? So based on that, so we can call it as differential pressure gauges, right? So otherwise, pressure gauges based on differential pressure, something like that. In fact, the next lecture, next week, we are going to discuss about flow measurement devices and instruments. There also we can have one type of flow measurement devices called differential pressure flow meters. Differential pressure flow meters. So starting from this, you can see like there are some interconnections between pressure measurement, flow measurement, and level measurement, right? There will be some, some instruments sharing the same principle between different physical quantity measurements, right? So it would be easy for you sometimes if you understand the concept, you can apply it to different physical quantity measurements as well, right? Okay, so this is a summary of what we discussed about the pressure types. So you can see that atmospheric pressure and gauge pressure and the absolute pressure, right? And also, I just included this slide for your reference. So I hope you can remember, but I mean, you don't have to remember all the unit conversions, but the major ones. An example would be, what is the relationship between PSI and bar, right? 1 bar is equal to how much PSI? That, of course, should be without referring to a book or somewhere, you should be able to quickly get it, right? So some important things like that you should remember as an engineer, but others, all the things you should not. You can refer this table even in the exam if required. The other conversion tables, if it is required, to be given. But the major ones you should keep in your mind. So and understanding about different pressure units, right? That is important, very important. Most of the cases you have to convert some in some cases if we discuss examples, right? The other question is, most of the students have this question. Before moving to the types of instruments, I would like to discuss about this also. What is the relationship between pressure and stress, right? So some students think like, because stress, you have learned about stresses, different type of stresses are there. And stress is also the unit and the dimensions of stress is also same like pressure, almost the same. So some people misunderstand that stress is equal to pressure, but it is not that. Pressure is a property of fluids, and pressure cannot support a shear. I hope you know about shear forces, right? Or maybe in stress, in fact, there are different types of stresses, but we don't have different types of pressures, right? I mean, we have like a static head, dynamic head, and something like that, static pressure, dynamic pressure like that, but we don't have tensile pressure, we don't have shear pressure. So stress is a different parameter, different physical quantity. But there will be some relationship between stress and pressure in another way. That is, in fact, stress is not relevant to discussion of pressure, but sometimes we use strain. There is a relationship between stress and strain, you know, but we use, and also strain has a relationship between force also. So force has a relationship between with pressure. So we can use the strain sometimes as a measurement of force and pressure. So in that case, when we are discussing about strain gauges, I hope there is some relationship, but totally stress will not affect on pressure. So you have to clearly understand that part. Don't misunderstand or confuse with stress and pressure, right? Then standard atmospheric pressure, again, you already know, but you should have some understanding, or like the values. in different values. So if, of course it is 1 atm, and how much is from millimeter, mercury millimeters, or maybe another like PSI or something. So you should have some direct values with you after a certain practice, right? Then we will start the types of instrumentation. The first type is hydrostatic gauges, right? You know that we discuss about the static head and static pressure, and if there is a kind of a fluid or a liquid there is hydrostatic pressure, right? That of course we have learned. So you can use this hydrostatic pressure relationship. It's true that pressure is equal to height multiplied by the density and the gravitational acceleration. So h rho g. So there is a relationship between the height and the pressure. So you can use this. I mean, you can this relationship as a gauge, and with the the height can be scaled based on the pressure applied on the liquid or the fluid, right? So you can see in the this slide for the same pressure, even though the container sizing and shapes are different, it will give you the same height, right? So that is, of course, you already know, right? But we can use this even you have learned about manometers. So these hydrostatic gauges are called as manometers. You have learned about manometers in your advanced level classes, I hope. Even in the laboratories and all, also you use manometers. In fact, manometers are used as industrial instrumentation also in chemical and process plants, chemical process plants, right? So there are different types of manometers. One is U-tube. U-tube, you know, U-tube means not the website. I mean the U-tube, U-shaped tube. So that is used for pressure measurement. And the difference between the height difference between the two sides of the U-shaped tubes. So you can find out the measurement for the pressure. And also another type of manometer is reservoir type manometer or well type manometer. So at there the sizing is different. In U-tube it's equal size in most cases, but in reservoir type one side would be a reservoir, other side would be a small tube, right? And then incline manometer is there. So that's another type, and mercury float manometer, right? So these are 4 types of manometers that use same principle, but the shapes and the way it is used is different, right? Then actually I'm not going to discuss in detail about manometers because you know already Manometer Basics. And if I tell you as facts, if you get the U-tube manometer, you can see a picture here. You can see where the U-tube manometers have been used in the industry to measure the pressure, right? So there also you measure the difference of the pressure or differential pressure between the 2 points, the 2 flanges before and after the U-tube, and then the height difference is measured. So electronically even nowadays it is, I mean, you can fix the control circuit with, you can convert the height, you can measure the height and convert it into an electrical signal. Then you can electronically obtain the reading, right? And also you can control. So that is the importance of U-tube manometers. There are no moving parts, and you don't require any calibration because nothing will be changed except the U-tube is corroded or after some time something happened, right? But sometimes a specific liquid fluid is used inside the U-tube, so that avoids the corrosion or something. So most cases it is not calibrated. Then from the basics, pressure is equal to h rho g. So in that case, you need the the conversion of the pressure to height. You need the standard properties of the liquids. So then you can use the accurate values from the standard values. Then only, so you have to sometimes in developed cases like this in this picture it would be okay, but if you want to introduce a very simple manometer type pressure gauge, then you need these property values to convert the values and find out the exact pressure. So that makes some difficulty because you have to do some calculation, or you have to scale the indicator or something based on the certain values. Then that those values, if they are not accurate, that these values will affect the accuracy of the instrument, right? That is why the manometer is considered as a very primary pressure instrument, right? Then, of course, you can understand that like this in another case, one side can be fixed with the gas, right? Another one is open to atmosphere. Then you can measure the gas pressure also. So it's not always, so the liquid that is used in the U-tube will be another liquid that doesn't affect to the corrosion of the U-tube, and the gas pressure can be measured. So both gas pressure and liquid pressure can be measured using manometers, right? Then you can see the the difference, how it affects. So if greater pressure applies, the U-tube, the water level will go down, and it goes up when the pressure is low. So that is the relationship, right? So and the other thing is, most of the cases the liquid would be mercury. Then I hope you know why mercury is used in most of the cases, because it has good properties on pressure measurement as well as temperature measurement. So if you use mercury, the value can be directly taken in millimeter of mercury. That is the pressure unit, right? So that is one reason. And also you can get the gauge pressure from manometers, right, rather than absolute pressure. So gauge pressure will be positive when the unknown pressure exceeds atmospheric pressure, right? So the pressure that you want to measure is above the atmospheric pressure. You get the measurement as positive as well if it is a vacuum or a negative pressure, or if it is below the atmospheric pressure, it will give you a negative value. Even the vacuum can be measured in that way, and every time you have to find out the atmospheric pressure and compensate the value to get the absolute pressure. So it will work like this. In fact, so you can see this animation, how lower pressure and higher pressure apply. So higher pressure, the level goes down, and lower pressure, the level goes up. So where one side is kept at atmospheric pressure, right? That is the understanding of manometers. Then there are variations of U-tube manometers. You can have two mainly, with both manometer legs open to the atmosphere. Then the fluid levels are same. I hope these are simple things you can understand it by yourself. With an equal positive pressure applied to one leg of each manometer, the fluid levels differ, but the distance between the fluid heights is the same, right? Then the next type, we are still discussing about manometers. The reservoir type manometer, we discussed about U-tube manometers, because even though that is the most primary one, it is always used. That is why we discuss a little bit more. And it is easy also. Then well type. So one leg of the U-tube manometer is replaced with a large diameter reservoir or well. So then the pressure can be applied in differential pressure can be found, and the height of the other leg, the single leg or the tube of the this manometer can be used to measure the pressure. So the relationship between the differential pressure and the height and area of the tube have been given as an equation here. You can understand how it came also. That is nothing but the pressure to height relationship, right? Then I hope the discussion about manometers would be enough, because it uses the same principle and it is simple, right? But I would like to discuss about pressure sensors now, because that is the most important part in this lecture to be learned by yourself. Then I would like to memorize the control circuit, or how process measurement happens, right? So we discussed this in the first lecture. We have a sensing element and a transducer or transmitter stage, as well signal condition stage, and then finally to be recording and display stage. So here what we replace is sensing element. So we will have several sensing elements for pressure, right? Pressure is one physical quantity. For that we will have several sensing elements. Of course, it is really difficult to use manometers, U-tube manometer, well type manometer, other type manometers. It's little difficult, quite difficult to use as to be used as sensing elements, while there are many other techniques, many other principles where we can develop sensing elements for pressure, as it can be used as pressure sensors with the transducer or transduction element, and we can connect the pressure measurement system or pressure measurement device into a real control system or electrical measurement system, like digital system, right? So these sensing elements are, first one is Bourdon tube. There are different shapes of Bourdon tube, but simply we can say Bourdon tube. So today we have to learn about what is a Bourdon tube. Then diaphragms. I hope you have heard about diaphragms, but we have to learn. Then capsules, bellows, and other types of sensing elements, right? So except diaphragms, is little different compared to other sensing elements, because other sensing elements provide a fairly large displacement. So all these sensing elements are related to displacement versus pressure relationship. So if I simply tell you what happens is, when pressure is applied to this sensing element, an example would be if I take Bourdon tube. Bourdon tube means the name Bourdon is given by the person who invented that. That is a small tube that undergoes to a certain motion or a displacement when the pressure applies on it, right? Similar way it happened for the capsules, bellows, and diaphragms. But diaphragms, the movement or the displacement is very little compared to others, right? So this creates some problem with diaphragms because since the displacement is very small, how to relate it to pressure, it has some effect on measurement accuracy or sensitivity. But of course, I will discuss that part when we come to the diaphragm. Actually, this barrier has been overcome by the technology, and now, of course, in most cases, I mean, out of all these sensing elements, the most popular one is diaphragm and Bourdon tube, right? It is always used, even in Sri Lankan process industry. After you go to industrial training or something, if you, have a thorough look on inside the plant equipment, you can see many Bourdon tube and diaphragm type and other type of sensing elements they are using in the industry, right? So first, I would like to little discuss more about the principle. So if we take a capsule or a bellow or whatever it is, what happens? You can see in this picture, when pressure is applied on this element. So this is the capsule means like, capsules that we use in pharmaceuticals, like that. Its shape is like that. It has inside there is some hollow area. When the pressure is applied on that, the surface of that capsule or the diaphragm or the bellow is moved. So we have to use a special material for this, which can have, so this can be called as a membrane type, right? So it's kind of a membrane type material that displaces with respect to the pressure, right? Then of course this motion can be measured, right? So there is a direct relationship between this motion and the applied pressure. So that is the thing, and you can use springs. You know that springs are used in any mechanical system to aid the displacement. So spring can be used to keep that motion and relate that motion with the pressure. So sometimes springs are also used with these. What happens is first capsule or bellow or diaphragm attached with the spring. Then the spring will take that motion, and you can it's easy to obtain that motion from the spring to another indicator or something to be indicated the pressure measurement, right? Okay, so first is bellow, right? It is made of, mostly the bellow material is bronze, stainless steel, or beryllium copper, or monel, or some other metal, right? So no, these are measured by metal, but it is still flexible for the pressure. So it works as a membrane, even though it is made of a metal, right? So the movement is proportional, as I said, to the number of convolutions. Sensitivity is proportional to the size, right? So it has a range. All these equipment have a range for the measurement that depends on several other aspects also. So in this case, bellows, you can say the range is between 0 to, around very small pressures like 5 mercury millimeters up to 2000 psi or something. 2000 psi means around more than 10 bar, right? More than 10 bar, around 12 bar or something, 12 bar, 15 bar or something, right? So the accuracy is also within 1% span. So bellows are a good type of sensing elements in most cases, right? So how it works? The bellows are working like this. It's like this. I hope you can see from the animation how it really works. Right, when pressure is applied, this is the bellow, and you can see what I told you previously. The spring is also attached to it to obtain the indicator. So like this, in some pressure measurement devices, I mean, you can only see the circular shape scale only, but inside it is having this small part of bellow, right? Then you just rotate and connect it to the line, the pipeline. Then if the gas or liquid or something flows through the pipeline, it will give this movement to the indicator, and you can see the pressure. That is how it works, right? So then the most important one is this actually Bourdon gauge, right? Bourdon gauge. So Bourdon gauge is a key concept is pressure difference across different areas of inner and outer surfaces causes a crescent to flex. Forget about the difficult words. Here crescent means a kind of flexible tube, right? It's very small. So even many of the pressure gauges that you see in the industry are also Bourdon gauges in most cases. I think if you go, after you go training there in a certain training place, if you can talk with the maintenance people, then you can obtain an old Bourdon gauge tip. I mean, whatever the pressure gauges in any company, there are pressure gauges that are out of service. I mean, it's not working, so they might have them. So you can get them and disassemble and check how the inside is working like that. But of course, it's really difficult for me to explain in this mode how it really works. But I hope you can understand from the pictures and animations. So in this picture, as you see, when the pressure is applied, this tube is moved, right? So I will show you in an animation like this. It works like this, right? So when the pressure is applied, so if you can see my cursor, right? So pressure is applied from here, and there is a pinion and kind of mechanical arrangement. So this arrangement is changing. Sometimes it doesn't use a pinion like this. It might use a geared sector like this in the other picture, as other picture shows you. So what happens is it will have a kind of deflection in this tube. So with the deflection, you can have the movement in the scale, the indicator, right? So that is how you measure the pressure, right? So this whole Bourdon tube, mostly this can be found in the industry, right? Then there are several types of Bourdon tubes. What we saw is in the previous slide, what we saw is the C-type tube, but there are spiral and helical type. Whatever the shape only changes, but the principle and how it works is same, right? Then I want to talk about diaphragms. They are these diaphragms, bellows, and bellows already we discussed, and capsules. All these are commonly called as capacitance based pressure gauges, or capacitance pressure gauges. So the principle is deflection of a certain membrane is obtained. So a diaphragm is a type of membrane. It can absorb the pressure and works as a capacitor. What happens is normally capacitor is, in electrical terms, capacitor is one that absorbs it can keep the electrical conductance, right? So like that, in pressure capacitor means it can hold the pressure and convert it into another form, like the deflection or the change in displacement or something like that, right? So normally a capacitance manometer, you can be called as capacitance manometer also. Sometimes it is used like this, but I will explain this later also. This has some link with this resonance wire gauge as well as ionization gauge. Similar concept is there. But anyway, what happens here is there's a diaphragm. When the pressure is applied on the diaphragm, it can work as a capacitor, pressure capacitor, and then you can the displacement can be linked with strain, right? Then strain has, it can be converted into a kind of resistance. So how it happens is actually I haven't taught you yet the strain gauges, but if I simply explain you, if a strain gauge is fixed here, right? What happens is there is an electronic circuit with the resistors, right? So it is called bridge circuit, a very simple one that you have learned. the Wheaton bridge, right? So that type of circuit will be there. So the displacement can be converted as a resistance of a certain resistor, and then the voltage can be changed with the resistance. Then the output voltage from the bridge circuit is a function of the resistance change due to the strain in the diaphragm. Strain happens with the displacement, right? If something displaces, the relationship between the displacement divided by the original length is called strain, right? So that strain or the displacement has a relationship with the resistance change, and that has a relationship with the voltage. So finally, you can from the electrodes or using resistors, you can measure a certain voltage, like you did in the thermometers, thermocouple thermometers, right? So finally, you will get the the measured value is voltage, but there is a relationship. Based on that, you can scale the thing and measure, or otherwise you can use that voltage output for a certain electric circuit or electronic circuit to control or the digital measurement. So this is really important because in another lecture I will discuss in detail about strain gauges, because it's really important, because strain gauges extend the discussion into load cells also. Load cells are also very important for you when we talk about mass measurement or weight measurements in the industry. Load cells, right? So when we discuss about load cells, we will in detail discuss about strain gauges a lot, because strain gauges are important in modern transducers. So even though here the diaphragm or a bellow or a capsule or a Bourdon gauge are used as the sensing element, we need a transducer to convert the signal. So that transducer would be a strain gauge, right? So simply understanding that way at the moment, right? So if further discuss about diaphragms, the diaphragm is a flexible membrane again, if I tell you. It sometimes looks similar to the Bourdon tube, but and also sometimes Bourdon tube and diaphragm both are used in certain cases. So there are many other ways, and different types of diaphragms are there. Flat diaphragm, corrugated diaphragm, that is based on the shape of that. So diaphragm is very important. Another fact, if I tell you, diaphragms in the old days, they used metallic strain gauges with diaphragms, but it was not successful that much. But nowadays, it is used the semiconductor materials or piezoelectric materials. Then that is how they overcame the previously I told you about that diaphragms. There is some problem with low output because this displacement in membrane materials is fairly low compared to the Bellows or capsules. So to overcome that, the technology has used and changed the material into a semiconductor or piezoresistive or piezoelectric materials. Then even though it has a small displacement, it has a high sensitivity, right? That is how they overcame the problem, right? Then if I give you another animation, it works like this. So it has a small movement, and again the pointer is working, right? So strain gauge, how strain gauges are applied in the diaphragm type diaphragm type pressure measurement devices is like this. So you can see the diaphragm at the bottom and here, and then you have the strain gauges there, and you can convert this the displacement change into the resistance change in this strain gauge, or after that it will be finally measured as a voltage change, right? So it says that more than one strain gauge. Of course, there will be several strain gauges used, and not only the pressure, sometimes the load also can be measured by this if you use a strain gauge principle there, right? So then some other types. So we discussed the main types of ones, the pressure devices. They have Bourdon tube, diaphragm, capsule, and bellow. But there are some other techniques like fibre-optic pressure sensors. What happens in fibre-optic pressure sensors? They are sometimes called as photonic pressure sensors. So now it is the discussion is about strictly about pressure sensors. In that case, of course, a diaphragm is used, but what happens is there is an emitter and a detector. So a certain kind of the fiber optics, normally what it takes is a light beam or something. So light beam emitted from the emitter, and due to the light beam, the diaphragm has a certain due to the pressure application, diaphragm has a displacement, and this light beam can reflect with respect to the displacement. So there will be a relationship between the displacement and the light beam. So the light beam is detected by the detector the reflection through the displaced diaphragm, right? Then with respect to the displacement in the diaphragm, the output signal to the detector will be, the reflection will be changed, right? So they use this technique, so and use fiber-optic pressure sensors with emitter and detector, right? Capsules already follows the same principle like Bellows. If I show you this one, it is the same thing, and you can see in the picture here, you can see this is how it really looks outside. It fixes to a kind of a pipeline or a vessel, pressure vessel or equipment, any equipment to measure the pressure. So it fixes from here, but you don't see what is it. It really looks like a capsule or a tablet, but inside it has this kind of a element that displaces with the pressure and shows you the pressure indication in the scale with the pointer, right? So if we compare this elastic element or the capacitance type or the displacement type pressure gauges, capsules, bellows, and Bourdon tubes, if we compare, the Bourdon tube has a very high pressure range compared to bellows and capsules, and as well, Bourdon tubes can be used in most of the industrial applications. In some cases, bellows and capsules are not used with the application. And the other thing is the price. The price is cheaper for Bourdon tube compared to bellows and capsules and diaphragms, right? Because you have to use a specific membrane material for capsules, bellows, and diaphragms, while Bourdon tube will be simple material, right? So due to these reasons, most of the cases, industry select Bourdon tube with the cost and other stuff. But of course, in certain cases, sensitivity is high for capsules and bellows. So sometimes you have to use capsules and bellows if you really need that. So you have to make a choice of pressure measurement devices by thinking all these aspects and matching your requirements, right, in the industry when you have to select. Then there are some other types of pressure gauges. One is dead weight pressure gauge. So we learned about dead weight or null measurement in lecture 2, I guess. Actually, what happens here is, you can see the number 8 in this picture, right? If I enlarge it, number 8 here, this part. So this is where the pressure enters, right? So this is the point that we fix it to the pipeline or the vessel, right? Then what happens is this number 2 part, this part is shown enlarged here, right? It is shown enlarged here. So what happens is when the pressure comes from this, there's a small piston here. So this goes up and down. So this goes up, and that matches. So these are some weight. So these are kind of some weight pieces. So these pieces are put from here, and due to the pressure, this side, the piston movement, this side, so they balance. So what you have to do is you have to add the weights at the top and balance it. So when it balances, you have another manual piston pump here, and you can manually pump, and at the balance point, when it is called null point, which cancels the pressure force and the weight force cancel point, can be obtained here in this indicator, right? So please try to understand what my explanation. Then another type is potentiometric-type. Potentiometric means you have heard about potentiometer. Potentiometer is again, it changes the displacement or the resistance change into a voltage. So based on that principle, combined with diaphragms, capsules, or bellows, you can have potentiometric-type pressure sensors also. So these are different types of pressure sensors. Actually, you have to learn about pressure sensors like this. You should have some idea about different types of pressure sensors, because if you really have to work in the control side, or maybe one day you work as a process engineer, definitely you should have some idea about pressure sensors. And bellow is fixed with another spring or something, and you can convert it into Bellows resistance transducer, right? So that's another type. So like that, there are several sensing elements and transducers developed based on the basic sensing elements. Another one is inductance type transducers, right? So that there also diaphragm is the sensing element, and it converts into another form. Then you can together use as a transducer, right? Then piezoelectric pressure devices. Then use a piezoelectric material, and you can convert your pressure into a kind of a charge, right? Electrical charge, right? So then you can measure it, right? And another is resonant wire. So these are new types of, actually you can say these as transducers rather than sensing elements. It combines everything, and final output will be an electrical output that can be fixed with the signal conditioning stage and results monitoring or control loops, right? So unknown pressure is applied on a resonant wire, and then that resonates the frequency of the pressure. Due to the pressure, the resonance will happen. You have learned about resonance, I guess. So this wire is having some vibration and giving a certain frequency. That frequency will be matched with the electrical signal, right? Then oscillator will be there. It amplifies the signal. So it is like a pressure converter to an electrical signal. So this is another type of device, right? Then ionization gauge. Ionization gauge also is very important when you have to measure very low pressures, vacuums also, right? So they use an anode and cathode. An unknown pressure applies. Then due to the pressure, there is a gas inside. That gas ionizes, and it creates a certain electrical current or voltage difference between the anode and cathode, right? So then ionization happens inside. Then one filament is heated. Then with the pressure, there will be a different relationship between the ionization and the ionization, the voltage created due to the ionization and the pressure applied, right, on the gas, right? So you can see that ionization gauges can be used for very low pressures, right? What is intelligent type instrument? Intelligent type means, intelligent pressure measuring instrument means, in fact, you can have a microprocessor attached to the pressure measuring devices, right? Not only pressure, you can have intelligent others also, intelligent thermometers, intelligent flow. We will discuss next week about intelligent flow meters also, intelligent level meters also. How it becomes an intelligent instrument is adding a microprocessor. Then what happens by adding a microprocessor, it will have, normally so far what we discussed, we had in the beginning we had sensing element, then sensing element mixed with another thing and created a transducer. So maximum case would be we have a pressure transducer, which can be directly fixed to a signal conditioning stage. But in intelligent instrument, everything is combined in one. So of course the sensing element would be a diaphragm or a Bourdon tube or a Bellows or a capsule or whatever sensing element, but it comes as a single unit connected with microprocessors, transducing stages so anyway there, and signal conditioning with microprocessor and output measurement. Sometimes everything is there, completing the entire process measurement, the entire process measurement diagram. So then this can be directly used. Those are called intelligent pressure measuring instruments. So it can improve the sensitivity. It can, adapt to the system. So we can use a single intelligent type pressure measuring instrument into several applications. It can adapt with the application, or it can adapt with the measurement ranges, sensitivity, whatever the environmental effects on the instrument. So we can cancel them by adapting it. So like that, many functions are available. So that is why it is called intelligent pressure transducers rather than simple pressure transducers, right? So at last, I would like to compare strain gauges, capacitive sensors, potentiometric, resonant wire, piezoelectric, magnetic, optical. These are the electronic pressure sensors. It is compared in this picture. You can see in this figure that the best positive type, best temperature range, the pressure range is there for strain gauge and optical type, right? While for vacuum or the negative pressures, low pressures, resonant wire, potentiometric, and magnetic type, capacitive type. Actually, capacitive type sensors, like the major ones that we use. Why diaphragms, Bellows, capsules, Bourdon tubes, those are popular because you can see in this both negative and positive, fairly good range is there for that. So that is why capacitive and strain gauges are mixed and used. Of course, resonant wire is also is popular nowadays because it also matches both negative and positive pressure measurements, right? One important thing I forgot to tell you is what is the general pressure range that we focus to measure in normal industrial applications related to our field. That is actually in positive side. Even here also you can see positive side from atmospheric pressure to 7,000 bar, right? So you can see 7,000 bar is somewhere here, right? Somewhere here. Right? Somewhere here, right? So this is the 7,000 something, right? So you can see, so this is the normal positive range, right? So this range is almost addressed by every device, right? So that is the normal pressure measurement range in the industry. Okay. So this is my lecture today. Have a nice day and stay safe.